Hi grade 11s, my name is John. Good to be with you again. Today's section on physics consolidation. What we're going to do is we're going to take a look at all the physics sections that are really important, that you need to make sure you've got them down and you understand the principles. We're going to be working through some past paper exam questions, making sure that you've got a good foundation from grade 11 work moving into grade 12 work. So let's see what we're going to focus on. We haven't been able to focus on all the physics for grade 11, but we're going to pick up the important ones. So here are the key sections that we're going to be looking at. We're going to start by looking at electrostatics. Now this section we've chosen because it is important for grade 12. In fact, all the electricity is important for grade 12, capacitors as well, and circuits. So remember that these sections move into grade 12. So you're going to need to make sure you have a good grasp of them. Now, the next section is one that we haven't stressed too much. In fact, we haven't really dealt with any questions on it, and that's about the NP junction. So we're going to look at a question of that. We'll explain some of the theory related to that. Then we'll go on to an electromagnetic section, Faraday's law. This is foundational also for grade 12. You need to recognize when we get to grade 12, we're going to be dealing with motors and generators, and you're going to need to understand Faraday's law. So we will focus on Faraday's law. And then the last two sections are the sections on physics, which are obviously also important. These are mechanics sections, and they're very, very important for grade 12 work. So this is kind of a wrap-up of grade 11 work that is important for your exams, but it's also important that you understand these questions as you get ready for grade 12. Make sure that you keep your notes so that when you get to the section for grade 12 that you've got something to revise, and just check that you've got everything in place. Now remember as well that there are sections that we're not going to unfortunately be able to cover questions on today that you do need to know, and those are the sections in waves. You're going to need to make sure that you understand the ideas of sound. What you need to know for grade 12 is that with sound, pitch is related to frequency. So when you get a high pitch and it's high, then that's a high frequency. When it's a low pitch, then that's a low frequency. So you need to know that relationship. You will also probably be good to know that loudness relates to amplitude. Also remember that there's a relationship between frequency and wavelength, and we write that as the wave equation, where we say the speed of the wave or the velocity of the wave is equal to the frequency times the wavelength. Now, for your grade 11 exams, it's also important that you make sure that you have got the other aspects of wave, sound, and light quite well familiarized. You're going to need to know the properties of waves, including reflection and refraction. Now, these are important in terms of lenses and optics. And unfortunately, optics doesn't take us very far into grade 12. We don't need to revisit that, but it is important for grade 11. So be aware and make sure that you revise those sections on optics, which I know came quite recently. So be very careful about those sections. But now let's focus on electrostatics. We're going to start by looking at some previous exam paper questions. Now, as we go through these questions, we're going to pull out the important concepts so that you can revise them. Now, hopefully you've had a chance to look at the questions. Let's see if we can sort these out together. question number 1 says the following. The diagram below shows a small metal sphere, P, on an insulated stand. So we recognize it's insulated. So that means that the metal is at the top here and it's insulated. The sphere carries a charge, and it gives you the charge of minus 4 times 10 to the minus 9 coulombs. Remember, the unit for charge is coulombs. And it's a very big number. When we are dealing with coulombs, you generally have to make sure that you've got SI units with these type of questions. Over here, they've given it to you in SI units, but you need to make sure that you can do the conversions, because normally they're going to give it to you in something called microcoulombs, which is times 10 to the minus 6, and nanocoulombs, which is times 10 to the minus 9 coulombs in each of those cases. So make sure you can do the conversions. Milli is times 10 to the minus 3, not commonly used, but make sure that when you're dealing with electrostatics that you know how to do the conversions. That's just an aside. So let's go and have a look at the question here. It says, what we're required to do is to draw the field pattern around the sphere. Assume that no other charges affect this pattern. So we've got one charge, and we're going to draw the field pattern. So what is this idea of a field? Remember, when we have something that has got a special property, in this case, it's a charge property. In your grade 10 work, you would have done with magnetic properties. And in grade 11, we've also done with magnetic properties. All of these are examples of non-contact forces. So where we get a charged object, so there's the charge, negatively charged. The region in space, and notice it's not just in 2D, but it's out over here as well, and it's behind the screen as well. It's all over. Goes in 3 dimensions, but we represent it as a 2D diagram. And what we're saying is, in the space around the charge, there is a region of influence. This space will be influenced by this charge. If we place a little test charge, positive charge, that positive test charge will give us the direction of force that will be exerted on that. If it was a free to move test charge, little test charge, positively charged, and if it was free to move, in which direction would it be moving? Well, you should remember that from electrostatics, there is a law related to attraction and repulsion. You should remember that like charges repel, and unlike charges do what? They attract. So if we do this test charge, what we're going to find is that there is an electric field that radiates out. Straight lines where we draw and say the direction of this field is going to be the direction of the force. So there's a positive charge, there's a negative charge. This negative charge is going to attract that positive charge, so the field line pattern is going to be inwards. We draw the straight lines to indicate how they're moving. So I'm just going to put a few in. There we go. Put the arrows on them so that we make sure that we've shown the direction of the field. And because it's a negative charge, the test charge is always positive. We can see there's the field line pattern. Now, you need to revise your field line patterns. It's a question that's often asked in exams, either to draw for a positive charge or a negative charge or a combination, 2 negatives, 2 positives. Go back to your notes and make sure you revise it. There is another question that I just want to highlight here. This is a radial charge. It tells us that it is changing, and we know from Coulomb's law that the force is going to be equal to K Q1 Q2 over R squared, which tells us there are 2 relationships that you need to know. That the force is directly proportional to Q1 times Q2. So if you double the charge of one, you're going to double the force. If you double the charge on both, then that's 2 times 2 times, which will give you 4 times the force. The second relationship that you need to be aware of is that the force is inversely proportional to the square of the distances between the centers. And that's often asked. So if you double the distance, you're going to quarter the force. Please make sure you understand those relationships. Notice as well that that means that if we go far away from, the further we go away from the big charge, the mother charge, then the weaker the field gets. And we can see this by looking at the field line, and we say, okay, if I draw a rectangle around there, that rectangle has got 2 field lines crossing through it. When there are more field lines crossing through a region of space, we say that field is strong. But now watch what happens if I select that and I move that region of space out over there. Can you see now there's only one? That tells us that the field over here is a strong field, and it has depreciated. It's got weak. Same area, but over here it was stronger where the field lines were close together, and it's weaker the further we go away. And it gets rapidly weak. The force decreases, as I mentioned. F is directly proportional to 1 over r squared. So it doesn't take much distance for that field to diminish. Okay, remember one other thing, that although that's a non-uniform field, we call this non-uniform, when we have another situation, when we have 2 plates, and we're going to come on to some questions with 2 parallel plates. That second one wasn't exactly parallel, so let me redraw it. 2 parallel plates. Then the field line, and I'm just going to use a pen to draw the field lines here, are going to be straight lines. And they're going to be equally spaced. You need to draw them the same distance apart. We need to indicate the direction of those field lines, and they're going to go from positive. That's positive, and this is negative plate. Then they're going to go from the positive plate to the negative plate. They're equally spaced, and so the field here is known as a uniform field. So please notice the difference. This is a uniform field between plates, which means that a little test charge placed anywhere over here or over there is going to experience the same force. Very, very important. Over here, non-uniform field, this test charge, if it was moved over there, it's going to experience a bigger force. Over here, a very small force. Over here, a medium-sized force, and so on. In this field, uniform field, so it's going to experience the same force. Okay. Hope we've revised fields very quickly. Let's move on and see what the next part of this question asks us. And it now says to us over here, please calculate the number of electrons in excess on the sphere P. Well, what does excess mean? It's a strange word. It's not a familiar word that we use every day, but it means additional. In excess, often used in chemistry, but here it means over and above those that are already present. Now remember, every substance has the same number of protons as electrons. So the number of protons equals electrons, they cancel each other out. That's what makes this pen at the moment a neutral substance, because the number of protons equals the number of electrons. Now, excess electrons gives the metal sphere its charge. So we know that we've got excess electrons because we've got that charge. Minus 4 times 10 to the minus 9 coulombs of charge. So how are we going to get the number of electrons? Well, it's not too difficult, because we need to remember something, that the charge on every electron is the same. So the charge on one electron is the same as the charge on every electron. It's 1,6 times 10 to the minus 19 coulombs. A very small charge, but this is the only charge on an electron, and it's the basic unit of charge. We say that charge comes in packages. Charge is quantized. You can't get any charge other than a multiple of this number. So you could have twice this number, you could have 3 times that number, you could have 10 million times that number, but every charge has to be divisible by a whole number of this. So what we're going to do is we're going to say, let's take our total charge, and we're going to divide it by the charge on one electron, which is that number, and that will give us the number of electrons, and it has to be a whole number because charge is quantized. So let's do the calculation and use our calculator. Let's just remind ourselves we've got a charge of minus 4 times 10 to the minus 19. So the total charge over here was going to be minus 4 times 10 to the minus 9 coulombs. This is 1,6 times 10 to the minus 19. And get our calculator. We're just going to not worry about the negative because this will be negative as well. This is a negative charge if we wanted it. They're going to cancel each other out. Let's get the equals, what that's equal to, put it on our calculator and see where we go. 4 exponent minus 9 is the charge in coulombs divided by 1,6 exponent minus 19. And that will give us a whole number. Notice, it's 2,5 times 10 to the 10. 2,5 times 10 to the 10, write it down there. 2,5 times 10 to the 10 electrons. Excellent. Notice the importance of it being a whole number as well. It's exactly a whole number of 2,5 times 10 to the 10. Very big number, but it is a whole number. Okay, moving on. 1,3 says calculate the magnitude. Diagram has changed slightly. Notice what it says. It says a second sphere, T. Okay, so there's T. Second sphere carrying a charge of plus 2 times 10 to the minus 9 coulombs is placed 1 centimeter from P. So there's the distance. We can call that R. Notice it's not an SI unit, so we must change it to SI units straight away. And we're going to say that's 1 times 10 to the minus 2, because centimeters, there are 100 centimeters in a meter, changing it to meters. We've got this in coulombs, we've got that in coulombs, and we've got the diagram. Now it says calculate the magnitude of the electrostatic force that sphere P exerts on sphere T. Now, I want to just bring in some mechanics here. Notice that we've got a force exerted by one object on the other object. But Newton's third law tells us that if one object, body A, exerts a force on body B, then body B will exert a force of the same magnitude but opposite direction. And that you need to understand. This is an example of a non-contact force. They're at a distance. We could say the same thing about gravitation. And you should recognize that Coulomb's law is the equation we're going to use. If we were using gravitational calculation, we would use Newton's law of gravitation, which looks exactly the same in its formula. So over here, we're going to say F for Coulomb's law is K Q1 times Q2 over R squared. Now, have we got the things into SI units? Yes, we managed to do that. Now let's just substitute our values in. And what we're going to say is we've got 9,0 times 10 to the 9. That's our constant. You pick it up from the data sheet if you haven't learnt it. And then we're going to put our charges. Put them in brackets. It's easier not to make a mistake, particularly when you're dealing with exponents. We're going to say 4 times 10 to the minus 9. And then this one was 2, positive 2, times 10 to the also power of minus 9. Now, notice we were asked for magnitude. Now, I find that when I'm dealing with Coulomb's law, I don't worry about the charges. Even if they didn't ask for magnitude, magnitude is the direction, is without direction. So if they didn't say magnitude, then we would give the force, we'd have to say what direction the force is. We'll come and discuss that. But in the calculation, you don't have to say plus and minus for the charges. So that's why I've just written 4 there and 2 there. I haven't written minus and a plus there. We can sort that out afterwards. Now, what's the distance? Remember, I converted it. It was 1 centimeter, and I said it must be 1 times 10 to the minus 2. So I'm going to open brackets, 1 times 10 to the minus 2, and I need to square that. Make sure you write that in properly, and then pay particular attention when you come to do your calculation that you do actually square it. Now, it's easy on these new calculators because we can see the whole equation as you write it out. So let's do it. 9 exponent 9 times, and it was 4 exponent minus 9 times 2 exponent minus 9. Oh, that one didn't go minus, so let me just move it across, and I want to put a minus sign in front of it. So make sure that you've checked it. There's an error there, it didn't pick up the times. So we've got the top row correct. Notice how I'm checking, and I'm making sure that my exponents are all correct, the powers are all right. Now, what I'm going to do is I'm going to then divide this whole thing by something in brackets, and I'm going to put it as 1 exponent minus 2, because I changed from centimeters to meters, and I want to square that. So I want to square that. Now check that you've got the whole thing. The square is in, and you can go back and just check, do a check step. Look at your equation, look at what you've got. 9 times 10 to the 9 times 4 times 10 to the minus 9 times 2 times 10 to the minus 9 divided by the denominator, and we check that we've got the right units, and we squared it, and we say equals, and then check what that answer is. It's 7,2 times 10 to the minus 4. So 7,2 times 10 to the minus 4 newtons. Remember, force is measured in newtons, and we need to give just the magnitude. Now, if they didn't say magnitude, in this case, what would we do? Notice what it's saying. It's saying the force, that sphere P exerts on T. So look over here. P exerts on T, and what we would need to do is we'd say that because this is minus and this one is positive, we're saying that the force is towards P. It's attraction, because unlike charges attract. So if we weren't dealing with magnitude, this is not required for this particular answer, but we would say not just attraction, although attraction would be accepted, but I think you need to go further than that. You need to say the force of, this is the force of P on T would be towards P. Okay, I hope you understand the difference between magnitude, where you're only required to give the size of the force, and if they don't say magnitude, if they say calculate the force, then you must give the size, the correct unit, Newton, and you must give the direction, and that could definitely be a question on your exam paper. Right, now let's see what happens next. We're told the spheres are now brought into contact. Okay, they're brought into contact with each other and return to their original positions. So we were told they were isolated, they've touched, they contact, they move away. Here's an important principle, and I want to remind you of the principle, and the principle is called the principle of conservation of charge. Now, you might be jumping out your seat because you've heard of conservation of momentum and you might have heard of conservation of energy, but here we've got conservation of charge, which means that you can never make or destroy charges. The number of charges that you start with is the same as the number of charges that you must end with. So what we're required to do is to say, okay, we started, let's calculate the new charge. And what we'll start is, well, what did we have to begin with? What was on P? It will be the charge on P. So let me just undo that for a second. Right here, we're going to say it's the charge on P plus the charge on T. And then we're going to divide it by 2. Because let's think about it. This one has excess electrons. This one was positively charged. So it has a deficiency. It has less electrons than protons. So what's going to happen is they touch, electrons are going to jump across to try and neutralize. And then the interesting thing is they will spread out. You can't have a cluster of electrons all sitting at one end. No. They don't like to huddle together. They want to get as far apart from each other as possible, so they spread equally over the same surface. It's like icing a cake. When your mom ices a cake for you, your birthday cake, she doesn't put a dollop of icing on one end of the cake and leave the other end of the cake uniced. No, she takes a knife and she spreads it out evenly. So your little brother doesn't get a fat pile of icing and you get a little pile of icing. No, it needs to be evenly spread. So that's exactly what happens with charges here. So the calculation that we're going to do is we're going to say, well, let's add these two together and divide by 2. That's the way that we'll get the new charge on both objects. They will have the same charge on both. So where do we go? We're going to say, what was the first one? It was 4, and it was negative 4 times 10 to the minus 9, and this was plus 2 times 10 to the minus 9. So I hope you can see that if you have negative 4 plus 2, you're going to end up with 2, and you're going to divide that by 2, and that means that you're going to end up with 1 times 10 to the minus 9 coulombs. Notice here we've included the charge. So if it's negative, it's going to be neutralized. The negative charges are going to be transferred, as I explained just now. These extra negative ones are going to kind of cancel out that. That means we're going to get 2 left over, because that's what it is. Divide by 2 gives us 1 as the final charge on both of those spheres. Okay, and if we then go to the last part of that question, it looks like we've done it. So let's just make sure we've got this all sorted. Question 1, we first of all had an individual sphere, asked about the charge around it. Then the second thing, we brought another one together, asked about the attraction, Coulomb's law. Then the next thing, we said, what if they touch, move apart? We've looked at conservation of charge. Let's move on to question number 2 now. And question number 2 is also dealing with electrostatics, but in a different way. It deals with capacitors. Capacitors are really important that you know, and they're an application of parallel plates where there's a uniform charge. So let's have a look at the question. Here we go. We're saying, highlight the important information. A capacitor is an electrical component which can store electrical energy. Capacitors are used in many devices, electric circuits such as radios, cameras, flashes, computer keyboards, energy backups in computers and laptops in cases of power failure, time delay circuits such as alarm system, etc. So, where do we go? What is the primary function of a capacitor in an electric circuit? So now, when we've got a capacitor, we've already been told it is an energy storing device. And that, I think, is the important thing that we need to recognize. Its most important function is to store electrical energy. Does that by storing charge and we recognize that it's got a really important function as far as that's concerned. Let's look at the second part of it. It now says two plates are arranged to form a capacitor. Just highlight that. So we've got two plates, two parallel plates. The area of each plate is 0,02 meters. The plates are separated by 0,004 meters air gap. So let's just draw a picture before we do the calculation. What we've got is we've got two plates. One plate sitting there and one plate that sits below it. They're parallel to each other. My drawing isn't terribly good. I'm not a very good artist, but I think you can see it. In between here, we've got a gap. And the distance of that gap is 0,004 meters. Notice that is how much? 4 millimeters, another way of putting it. Now what we're told is the area of each plate, that should be squared, is 0,02 meters squared. Area is always squared, and we need to recognize that as the detail given. Now, what we're asked to do is to calculate the capacitance. Now, there are two formulas for capacitance, and you need to understand that you can use them depending on the information that you're given. In this case, we've got area is the gap, so we know that we've got capacitance is equal to the permittivity of free space, and area has a dielectric constant of 1, so we can put that in. We've got area and we've got distance, so we can use that formula. It is on the data sheet. So let's go and write it down, and we're going to say the following. We're going to say capacitance is equal to the epsilon 0 times the area divided by the distance. If we substitute these values in, look on the data sheet for the permittivity of free space. It's 8,85 times 10 to the minus 12. And now we've got area. We've got the area was 0,02 meters squared. So we're going to times that by the area, 0,02 meters squared. Don't double the area. It's just the area of the plate. Okay, now you need to make sure that you just substitute the area of one plate. We don't double it. We just take the area of one of the plates. Although both of them have that area, don't double it, whatever you do. And then what we're going to do is we're going to divide that whole equation by the distance. Now, what was the distance? It was, there we go, 0,04 meters. And notice in this case, this one is not squared, 0,04 meters. Check that your units are correct. We've got that all sorted. And now let's use the calculator. So we're going to say, clear that, 8,85 exponent, what was it? Minus 12 times 0,02 meters squared divided by 0,004. That gives us an answer of 4,425 times 10 to the minus 11, and that would be units of capacitance. But let's just make sure we round up, because that's a 5. We're going to do to 2 decimal places, so it's 4,43 times 10 to the minus 11. So here we go. We're going to say it's 4,43 times 10 to the minus 11. Now, make sure you put the units in. What are the units for capacitance? It's farads. Okay? And recognize that this is actually a very small number, and we could have converted that. Just let's make sure that we can do the conversion. If you had to convert to a unit that is a smaller unit, what would that be? Well, if we wanted to say nanofarad, then what we would write it as is, remember nanofarad is times 10 to the minus 9, so we would be writing 443 nanofarads. Of course, you could also do picofarads, in which case you would have to say this is going to be 1,000 times smaller, so it's 0.4 picofarads, the same thing. Okay, those are alternatives, but we always leave our answers correctly in SI units. These are the correct units, no little symbols in between them, recognizing that they're smaller, just easier to work with. Okay, let's move on, and we've got question number 2.3. Now, what it says is the capacitor is connected across a 500 volt supply as shown. So there is our picture of the circuit, and this is the 500 volts. So there's the capacitor. That's your capacitor. That's the positive plate, that's the negative plate, and we've got a uniform field between the two, and we've got a 500 volt supply. So now we're asked to calculate the charge on each plate. Now remember, we know what the capacitance is. We've just worked that out. We said it was 443 nanofarads, or 4,43 times 10 to the minus 11. We've got that, so we can use that. What formula are we going to use here? Well, we know that capacitance is equal to the charge divided by the potential difference. Notice that this is the second equation, and it's the one, they're both on the data sheet, but we're going to use this one here because we've used the area 1 to calculate the capacitance. What we're needing to do, write down the formula and then substitute. So I'm going to write in SI units 4,43 times 10 to the minus 11 from the previous answer is equal to Q divided by potential difference, 500 volts. So we're going to put 500 there, and all that means is that therefore Q is equal to 4,43 times 10 to the minus 11 times 500. What does the calculator give us as an answer for that? So it's that answer times 500. And we get 2,21 times 10 to the minus 8. Now 2,21 times 10 to the minus 8. Let's write that down. 2,21 times 10 to the minus 8 coulombs this time. Okay, make sure your units are correct. Farads for capacitance, coulombs for charge. Right, what else do we have to do with this? It says now, state two practical ways in which the charge stored on the plates of the capacitor can be increased. So now we're wanting to increase the charge, the number of charges. And we're looking for two ways. Well, have a look here in terms of these are practical things. We want to make sure that we can do them. So the one way of doing it is to change the potential difference. That would be really quite easy. Look at what's going to happen between, if we know the capacitance is a set value and we know charge over capacitance, so if this is constant, what are you noticing? If you multiply this one by 2, what's got to happen to the charge? It's also got to be multiplied by 2 because Q is directly proportional to V. Got it? Hope so. So that's the one thing. You could increase the potential difference. Another practical thing that you could do, or another thing that you could do, is you could change the dielectric. So instead of using air, if you were to use a different dielectric, so you could replace the dielectric. That means the stuff between the plates. Instead of using air, you used another substance that has a different dielectric constant, not one. Inserting a different dielectric, what's that going to do? It's going to allow the capacitor to store more charge. Now, another thing that you could do that's not terribly practical is obviously if you increase the area of the plates. A way of doing that is just connecting more capacitors, and that would obviously allow you to store more charge. So bear those things in mind. And the final question, I think, for this section is, what is the name of the insulating material which fills the space between the plates of a capacitor? Well, I've already said that. That's the dielectric. So we've got that, and we're ready to move on to our next question, which is question number 3. In this case, we're going to be looking at a circuit question. So here we go. Let's go for it. The circuit diagram below represents a combination of resistors in parallel and series. The battery has an EMF of 12 volts and an unknown internal resistance R. So there we've got the question. And we've got the circuit. There's the battery. Remember, the long line is positive. I always like to put the plus there and the minus. This is the internal resistance. It is in the battery. Now, we're told the EMF is 12 volts, and we've got this circuit. Notice, if you start at the positive plate, this will give us I total, because there's nothing going, it's only one route going to here. Here, the current could divide. There's a switch, so it can't go there at the moment. The switch is open. So really, we've only got a 6 ohm. This is resistor 1. And this one is resistor 2. And how are they connected? There's one pathway. Starting over here, there's one pathway that goes through that resistor, and then back to the battery. So it looks to me like you've got a series circuit. Remember, when you've got one pathway, one region that the charges can move through, those things are in series. And we need to understand what we do in series and what those principles are. So it tells us that the switch is open. The ammeter gives a reading of 1,2 amps. I'm going to write that in, 1,2 amps. And it asks us to calculate the total resistance of the circuit as it is at the moment. Now, we might start by thinking, well, add that one and that one. Ah, no, we can't add that one. We don't know what it is. So we're going to have to use Ohm's law. And Ohm's law, remember, tells us the relationship between potential difference and current, and that relationship is a constant. As long as the temperature remains the same, you need to make sure you learn Ohm's law. So the total resistance is equal to the total potential divided by the, what have we got? The total current. And over here, we need to then find what the total potential is. Right, now let's substitute into this formula. Remember, the total potential difference is going to be the EMF, and we've got that value. We know that that's 12 volts, and we know that the current was 1,2 amps, and if you do that, don't even really need a calculator to do it, but just in case, let's do it. And you're going to get an answer of 10. So let's write that down, and remember the units. We've got 10 ohms. So that's the total resistance, and we've done it by using Ohm's law. Next part of the question says, calculate the internal resistance of the battery. Now remember, when we looked at this circuit, we said that's in series, and it's in series with that. So let's first of all find the R external, R total external, which is going to be R1. This was R1, and that's R2. Add them together and see what we get. That's 6 ohms plus 3,6 ohms, and when you do that, you're going to get a value of 9,6 ohms. But we know that R total, which is equal to R external plus little r, is equal to 10 ohms. So how are we going to get little r? Not difficult. Let's substitute the values in. We're going to say that we've got 9,6 plus little r is equal to 10. So where are we going to get little r? Little r is equal to 10 minus 9,6, which you should all see is 0,4 ohms. Got it? Let's move on. So now it says the following. Switch S, that switch there, is now closed. How will each of the following be affected? Right only increased, decreased, or remains the same? So the first question is the total resistance of the circuit. Now I want to show this to you because although they didn't say that you needed to do a calculation, let's do the calculation. Let's make sure that we've got it so you can see it for future. So if we close this, then these two resistors become parallel parts of the circuit. Remember, our total resistance previously was 10 ohms. Very important. That was with switch, with S open. So now the internal resistance is not going to change. We know that's 0,4 ohms, and we are happy with that. So now let's calculate the new resistance, external. Well, the external resistance, or the total external, is going to be R parallel plus R1, and then we would, to get the R total, add in the little r. So let's start by doing R parallel. And what we know is 1 over R parallel is equal to 1 over R1 plus that second new one, and I'm just going to call it for safety's sake here R3. Okay, so we're going to use R3 over there, so 1 over R3. And put the values in, it's 8 and 6, so equals 1 over 6 plus 1 over 8. Is that right? Yes, there we go. And if you have to find the common denominator, you can do it in your head, or we can use the calculator. So we're going to go 1 over 6. Practice this. It's important that you know your calculator. Get up 1 over 8, and we can go equals, and there it is, 7 over 24. So I'm going to write that down because I want to show you what you're going to do. You're going to say 7 over 24, but is that R parallel? No, it's not. We must therefore say R parallel is equal to, we invert that. So we're going to say 24 over 7. Now, how do you do that on the calculator and how are you going to get your answer? Here's a nice button to do. We're going to say, there we are, x to the minus 1. That's the reciprocal, and it gives us the answer of 24 over 7. And if we want to get it in a decimal, we're going to say it's 3,43. 3,43. Okay, let's write that down. Equals 3,43 ohms. Now, remember we aren't finished. We must add in 3,6 plus that one. So we're going to get R external. R external is going to be 3,43 plus 3,6. Okay? And if you add those two together, plus 3,6 equals 7,02, 7,03. Okay, let's write that down. 7,03, and so therefore R total is equal to R external plus little r. The little r hasn't changed. This should be ohms. 7,03 plus 0,4, and I hope you can see that your prediction should be coming true, that this is 7,43 ohms. So what are we saying? As soon as you put something in parallel, You didn't need to do that calculation. I was just giving it as an example of how you would calculate something in parallel, just to remind you the important things is using the calculator and making sure that you invert our parallel. But notice, anything in parallel is always going to reduce the total resistance. In fact, R parallel, here's an important test that you need to be aware of, that R parallel will always be smaller than the smallest resistor in parallel. So this total here is going to be smaller than 6 ohms. Has to be. And that's how we know it was 6 ohms over there when it was in series, but it will, R parallel will always be smaller than 6 because of the calculation that we've just shown. And there you've got it. You can see that it is smaller. And so what we can say here, although it's just for 1 mark, we've shown it in a lot of detail. But now, make sure you answer the question. It says only write down. So if I was in an exam and I'd done that, I need to put a line through it, say rough working. And here, what's going to happen? How will each of the following be affected? Write down only increase, decrease, total resistance, decrease. Okay. Now, next one. Here we go. Interesting one. How's the reading on the ammeter going to change? Now, remember that the reading on the ammeter here was 1,2. And we now know that the total resistance is going to decrease. Work that out. Let's make sure that we've got this calculated, because we now know it and we can do it. I want you to do a prediction first, though. What do you think is going to happen? We've decreased the resistance. We are keeping the same EMF. What's going to happen to the total current? Well, you should really just be able to apply Ohm's law. And remember, Ohm's law, we can write in the form I is equal to V over R. Now, here you should be able to see it without even doing the calculation. What's happened to this one? You got it? This one went down. What happened to that one? This one was constant. The EMF didn't change. So if this one went down and that stayed constant, you're dividing by a smaller number means that one must have gone up. Let's do the calculation just so that you can be sure. And there was the external resistance. We must add in the internal resistance, which was plus 0,4, and we're now going to say that's the denominators. We're going to do our silly trick, and we're going to say let's put that as an inverse multiplied by the potential difference, which was the EMF, and if I remember correctly, the EMF is 12, so we're going to multiply that by 12. So that part is the denominator, that part's the numerator, and let's see what happens to the current. Hold your breath, 1,6. So when we substitute in our values, we see that the current does go with our prediction. We started with a current at 1,2 amps, and now we've calculated it to be 1,6. I didn't check the second decimal place, but 1,62, we can write that 1,62 amps. So you can see our prediction using the formula has actually been confirmed. Right, now I think it's time to look at our next question, which is an interesting section. We haven't really covered the theory of this, but I think we need to take a look at the question because it may come up at some stage. It does sometimes come into the matric exam, although not very often. It's that section of work on electronics. So let's go and have a look at question number 4 right now. Question 4 says, study the following diagram that is used in an investigation. Now let's have a look at the detail of the diagram. We've got a cell here. There's a light bulb. And here we've got a strange diagram that's got a label P, N, and depletion zone. Okay? Asks us to name the component that is connected with the bulb across the cell in the diagram above. Now, P and N are your clue, and depletion zone is as well. This is an electronic component. You should remember that where you have a PN junction, that happens in a PN diode. So we should be able to say this is a PN diode or junction diode. PN junction diode. A diode is an electronic component that allows us to control current in a circuit. It allows current to pass through in one direction but opposes the movement of current in the opposite direction. Now, the reason that a diode exists and it works is because of the property of certain elements to be semiconductors. And that's what this section is about. You need to understand the difference between conductors, insulators, and semiconductors. Let's just recap what the main properties are. We recognize that an insulator will not conduct electricity at low temperatures. At most temperatures, no conduction. At very high temperatures, you will get some conduction, but not very much. Whereas a conductor, typically a metal, will be, you will get conduction. It will conduct current at low temperature. But when you increase the temperature, you increase temperature, then the current decreases. You might get at very high temperature some conduction here. Not very often. But something like air is a non-conductor, it's an insulator. But we know that when you get a very high temperature, that occurs high discharge of charge, big potential difference, like lightning. You're going to get a discharge even through air, and air becomes a conducting material. So what are these things called? Semiconductors. Well, they tend to behave like insulators at low temperature. They behave as insulators at low temperatures. So at low temperature, they don't conduct. No conduction, no current. This is classical semiconductors. But at high temperatures, they tend to conduct. There is a current. They allow current to pass through. So they behave like conductors at high temperatures and insulators at low temperatures, which is kind of an opposite idea. So we need to recognize that the examples of semiconductors include silicon and gallium, and they're found around about the middle of the periodic table, group 4 in that region. So semiconductors are really important economically. We use them extensively in the electronics industry, and in fact, computing has been revolutionized because of semiconductors. Even your cell phone, your iPads, your musical stuff has all been revolutionized by this. So what we need to understand is that pure semiconductors aren't very good at doing their job. We need to do something to them. We sometimes do some mixing, and that's what our next question is about. It says, define the term dopant. Now, as I mentioned to you, what we sometimes have to do to semiconductor material is these are crystalline substances that are grown very specially in very special conditions. And what we try and do is we add a substance to it where we can increase either the negative available charge or what we call a hole, a gap. A positive charge. A hole behaves a bit like a positive charge. So what we're going to say about a dopant is that it's an impurity. It's an impurity that is added to a semiconductor to increase conductivity. So even at low temperatures, it will become like a conductor. Conductivity. Okay, so what we've got is this idea that these materials, silicon, germanium, gallium, they can behave like conductors under some conditions. They can behave as insulators. But if we add a dopant, it allows them to conduct more effectively in a particular way. Now, what's the next question? It says, looking at our diagram here, we've got a P area and we've got an N area. Different types of semiconductor material put together. The N material has got excess negative charges, so carries electrons with it because of the dopant that's been added here. And with the P material, it carries what we call holes. So, and that allows for electrons to move into it. The holes are represented as little, we think about them as kind of areas of positive charge that can move in the opposite direction to negative charges. And that's what this is showing you. The holes would migrate to the left where the electrons are going to the right. So what it's asking here is to name the two dopants and say clearly how each is used to change the properties of the main element in the components that are made up of. So let's start with the N material. Now, N-type semiconductor material, N-type material is usually going to have a dopant that is arsenic added. Arsenic is added to N-type material, and that means that it adds a free electron. Okay, so to the basic N-type material, we've added one or two or three small number of atoms that have this extra electron, and they form in the crystal where the other substance that the material is made up of, like silicon, doesn't have enough electrons to go around. Here it's got the same number of electrons as protons. Arsenic takes up the same space, and it's got an extra electron compared to the silicon. So that extra electron then is the dopant that is added. What about our P-type materials? Well, in our P-type materials, we use a different dopant. What we're going to use is we use gallium. Gallium, and the reason that we add gallium is because it adds a positive hole compared to the other substance that the P-type material is made up of. So those are the two dopants that are added to N and P-type. So in the P-type, we've got more holes. In the N-type, we've got more electrons. Okay, now it asks us to look at this particular thing, this particular circuit, and predict what's going to happen. Predict the effect of connecting the components in the opposite way. Let's just have a look at what's happening at the moment. We said that in the P-type material we've got extra positives, and over here we've got extra negatives. So if we look at this, there's the cell. Notice the long is the positive, this is the negative. So it makes sense that the negatives are going to be attracted to the positive, and that is going to cause the depletion zone to increase. So in this way, the positives are going to be attracted to these negatives, and we're going to widen the depletion zone. This type of connection is called reverse bias. And at the moment, what can we say? Well, it will get to a point that we will find that the light bulb will not shine. Okay? So firstly, there'll be I is going to be 0 amps, and there's no shining. Got it. What's going to happen if we do it in the opposite way? So now what we've got, and I'll just do this down here just to ignore what I've done. Instead of this being connected to the positive, instead of this being connected to the negative terminal, let's swap them around. So I'm going to just try and do it over here. Say, let's pretend that that now is positive, and this one is going to be negative. So I'm going to make this one negative. It's the opposite. Let me just erase these signs. What's going to happen? If we connect it in the opposite way, what's going to happen? Well, now, can you see what's going to happen is the electrons are going to be pushed in the opposite direction, and the holes are going to be pushed in the opposite direction. So the electrons are actually going to make the depletion zone smaller, and what will happen is some of the electrons will jump across here and start moving there, and some of the holes will kind of move in that direction, or we can think about them moving in that direction, which means that we're going to get a flow of charge. And as soon as you get a flow of charge, what have you got? You're going to get the current increasing, and this bulb will shine. And the result of that is that we don't call it reverse bias, but we call this forward bias. Predict the effect, and the effect we're going to predict is we're going to say that the bulb will shine. There will be a current through the circuit. And the explanation for that is that we are now in a situation with forward bias, and I've explained that, which you can add to. So there's going to be a movement of charge. The depletion zone is going to decrease. Depletion zone will decrease, decrease in size, and charges will cross the depletion zone, cross over. And so there will be a current in the whole circuit. And that's exactly what a diode does. It prevents charge moving in a particular direction, but allows it to move in another direction. So we've got that sorted out. Now, having just spent a few seconds on, or a few minutes on that section of electronics, please remember that you're going to need to keep some ideas about electronics. I know it isn't a very popular section. Some schools teachers don't teach it. I hope you're not in one of those, but read about it. It's really interesting. In your matric section of the syllabus, you might need to learn a little bit about light-emitting diodes, and that's why I've included this question in this revision overview of grade 11 physics. Right, let's move on. Question number 5, also an important section, and let's get going with it. Michael Faraday, self-educated physicist, great example for all of us. He discovered that when a magnetic field, when the magnetic field through a loop is changing, a current is induced in the loop. This discovery led to a whole lot of things and supplied electricity, and it's the way that we make electricity happen. Now here, while making study notes, Daniela finds the following question in her textbook. It says this. It says, a loop of coil with an area of 0,2 meters squared, the magnetic field at right angles to the coil has a magnitude of 0,15 Tesla. Calculate the magnetic flux. Now, you need to understand the terminology here. And the important thing is, what is this idea of magnetic flux? Well, it's not too difficult. We've got magnetic flux, phi is equal to B, the magnetic field strength, times the area. Cross-sectional area, these two are at 90 degrees, then we're okay. So let's just work it out, and what we're going to say is we've got the field is 0,5 Tesla, SI units are correct, the area is in meters squared, so it's 0,2. If we multiply those two together, we're going to get the correct answer of 0,03. Now we can put it as Tesla meters squared. That's one way of writing it, but the other way is to use the SI unit, which is a Weber. A Weber. Not a Weber that you cook on, but a Weber. And so there are the units for magnetic flux. And we've calculated phi. Now, let's see what else she says. She learned that a change in magnetic flux, important, is needed to induce an EMF in the coil, and decides to do an investigation. However, the only coil she has is 15 turns, and the magnet that she found is very weak. So what does it say? Explain how the following factors will affect the EMF induced in Daniela's investigation. Now, before we do that, let's just make sure that we remember what the Faraday law equation is. EMF is equal to minus the rate of change of magnetic flux, which we're going to write like that. Rate of change of magnetic flux, and we've included the number of turns. So explain how the following factors will affect the EMF if we change the turns of the coil to 15. Remember, we started with one coil, one loop, and now we're increasing the number of turns. So what's going to happen if you say EMF from here, the E value, is directly proportional to N. So if you increase the number of turns, what's going to happen to that? We're going to say it's going to increase. That's going to increase the EMF. Next part, using a weak magnet. Well, look, we know that phi is equal to B times A. So that tells us from that equation that E is directly proportional to B. So if we use a weak magnet, then we recognize that in fact we're not going to, if we change the strength of the magnet, we're changing the B value, and if we make that less, then EMF is going to be less. So EMF will be small or smaller if we use a weak magnet. Okay, so now, what did we say here? Suggest one way of increasing the induced EMF using the available apparatus. So here's something that we need to think about and you need to learn. Look at the equation again. EMF is equal to minus N delta phi over delta T. Now, what can we do to change it? We can't change the magnet. Although that we've only got this weak magnet, it's very weak. We can't change the number of turns. But what can we do? What can we do practically? Look at that value there. And I hope you can see that represents time. So the change in time, what does that mean? It means that as we are going to be moving the magnet into the coil, we can either do it over a long time or very quickly, over a short period of time, changing the magnetic field quickly. And so that would be the critical thing. So if you recognize changing the time, which in effect means this motion of the magnet, or the speed of the magnet, motion of the magnet. And what do you want to do? You want to make that small. You want to make delta T small, which means that you want to make this motion very fast. And if you do that, if you make the motion very fast, move the magnet in backwards and forwards very quickly, you're changing very quickly over a small period of time, then you're going to get a bigger EMF being induced. Okay, that was a quick brush up of Faraday's law, but we need to move on. And we're going to be moving on, leaving the electricity behind and moving on to that section on mechanics. So let's get going with the first idea, and that's momentum. And we've got a question on momentum and impulse here. We're told the trolley A of 10 kilograms moves east at a speed of 5 meters per second. And when it collides against a second stationary trolley of 6 kilograms, the trolleys separate after collision, and trolley B now has a velocity of 1 meter per second east. Calculate the velocity of A after collision. Now, remember what I said to you when doing mechanics, you need to, on the momentum, you need to draw a before and after picture. So I'm going to do just that, because Sometimes it's just a bit too much to read that without understanding it. So let's draw trolley A in green, and we're going to say this is A. What does it have? It has a mass of 10 kilograms, and it's moving at a velocity, initial velocity of 5 meters per second, and it's moving east. Notice it collides with the second stationary trolley, B. So I'm going to draw B in a different color. Let's make B pink. And the initial collision, the initial conditions of B is that it has a mass of 6 kilograms and it has an initial velocity of 0 meters per second. Now, what we need to recognize when you've got collisions, you've got momentum, conservation of momentum. First statement you're going to write in your book is that momentum is conserved. The total momentum before collision is equal to the total momentum after. So I'm going to start that process right here, having just sketched the initial condition. I'm going to say momentum before is equal to momentum after. And I'm going to now write down what the momentum is before. I'm going to expand it. I'm going to say A, the velocity, the initial velocity of A plus the mass of B plus the initial velocity of B. Let's substitute the values in from my diagram, and I recognize that I'm going to put in the mass of A was 10 kilograms times its initial velocity of 5 plus, go to the pink, we had a mass of 6 kilograms times an initial velocity of 0, and so we get the total momentum of the system before collision is 10 times 5, which is 50 kilograms meters per second to the east, because it was all going to the east. Let's take the east as our positive direction. Now, having got that, our next statement is momentum after collision is equal to 50 kilograms meters per second to the east. Now we know that. Now, having done that, I want to sketch the scenario after. The after picture. What does the after picture look like? Well, let's get a diagram over here, put some ground in, and see what the question says. It says, it collides, the trolleys separate after the collision, and trolley B now has a velocity of 1 meter per second to the east. Okay, so let's put the trolley B in. And this one, B, which has a mass of 6 kilograms, has a velocity of, final velocity of 1 meter per second in that direction. And we know that the other trolley A, we're not sure exactly where it is and in which direction it's moving, but we know that it still has the same mass, and its mass was 10 kilograms. We don't know what its velocity is, so we're just going to say final velocity is what we are trying to find. Got it? So let's now work out what the velocity is. We're going to do that by using that value and an expression for the final final momentum. So we're going to say we know that the momentum after is equal to the momentum of A final plus the momentum of B, mass of B times the final velocity of B, and if we substitute our known values in now, we know that this one was 50. We know the mass is 10. We know the final velocity is V, plus we know the mass of this one is 6, and its velocity was 1. So, how are we doing? Hope you've got it. 6 times 1 is 1. We're going to subtract that from 50. We're going to get 44 is equal to 10 V final. So therefore, V final is going to be 44 divided by 10, which is 4,4 meters per second. Now notice it's a positive answer, so we must say to the east. Okay, not sure how that's going to work practically, because it looks like this one has a bigger velocity than the one in front of it. So that might be a little bit of a problem. It might need to collide again. But it looks like we've got the answer correct. Let's move on and look at our next question. It now says, calculate the change in momentum of B. Let's look at the change in momentum of B. Now remember what change of momentum is. Change of momentum is the mass, the final velocity, minus the initial velocity. But we must make sure we've got directions very clear. And what we know is that initially, the initial velocity of B was equal to 0 meters per second. The final velocity was equal to 1 meter per second. So we're not worried about direction there. Let's say that's the positive direction. And what you're going to see is not too difficult a substitution. The mass was 6 kilograms. The final velocity was 1 minus 0. We substitute that in, which gives us 1. So the change in momentum is 6 kilogram meters per second. And this is to the east. Please make sure that you understand that both momentum and change in momentum are vectors. If they don't say magnitude, you must give direction in your answer. Right, what's the next part of the question? It says, what is the impulse on trolley B? Now, here's the interesting thing. The impulse is equal to F times T, which is the change in momentum. Which is what we've just calculated. So if I look at that carefully, it said calculate the change in momentum of trolley B, and here, what is the impulse on trolley B? And the impulse is exactly that. It's 6 kilograms meters per second to the east. Now remember that it's still F delta T. Last part of the question tells us the trolleys were in contact for 0,1 seconds. Calculate the force of trolley A on B during the collision. So what we've got is we've got the change in momentum, 6 kilograms meters per second. We've got the time, 0,1 seconds, and we need to find the force. Now, when trolley A exerts a force on trolley B, we need to recognize that trolley B exerts the same force, but in an opposite direction. So that's the principle that we're going to use here. We've got the impulse of B, and we're going to use it to calculate the force that trolley A exerts on B. And so let's just do it. We're going to say the force is equal to the change in momentum over the change in time. And in fact, this is an alternative definition of Newton's second law that you should really learn. It's nice and easy to say. We say that the net force is directly proportional to the rate of change of momentum, and that is Newton's second law, very clearly stated. We substitute 6 divided by the time, which was 0,1, and you're going to get a force of 60 newtons. 60 newtons towards B. B was stationary, which was to the east. If it had asked us what was the force that B exerted on A, we'd have to say 60 newtons to the west. And we're simply applying Newton's third law there. Right. We've got another Newton's law question now. Question number 7. Look what it says. Diagram A. Want to highlight. We've got diagram A. That's diagram A there. It says a person, this is A, pulls on the string connected to the wall. The force applied is 25 newtons. So I'm going to say 25 there. And then the next one, diagram B. This diagram, two people pull in opposite directions on a spring balance. So this is a way of measuring the force. And each person exerts a force of 25 newtons. So 25 newtons, 25 newtons. Right. In the direction that are shown. So name the pairs, the force pairs in each diagram. So let's just get a free body diagram to represent that. Let's say that's the wall, and we're going to say, well, we've got the force of A is pulling on the wall. So this is the string on the wall. And what we would recognize is that this is the force of A on the wall. There's no other force on the wall. But what we do recognize is if we've got the person A over here, then through the string, the wall is pulling on the person. And so we would recognize there's an opposite force. This is the force of the wall on A. Notice they're the same magnitude, but they're in opposite directions. So what about in diagram B? Well, in diagram B, we've got the particular thing is this end of the scale balance. And what we've got is we've got person B, or a person, pulls on the spring balance, 25 newtons. But what's happening here? There is a pull back of the spring of the system, and it's in the opposite direction, 25 newtons. So this is the tension in the string, if you like, and the tension in the string can be measured at either end, and it will be the same. The tension over there or the tension over there, it's the force that's being exerted by the person. And in exactly the same way, we can say at this end, we've got a 25 Newton force, but on the person, there's a force of 25 newtons. And so there you can see you've got every force always comes in pairs, because when you're dealing with a force, there are two objects involved. Object A exerting a force on object B, or object B exerting a force on object A. Let's move down, and it says, what is the force exerted on the wall in the diagram? So what is the force exerted on the wall? Well, it's not too difficult to see. The force is through the rope, and it's 25. From the question, 25 newtons. Okay. Now, here's the one that a lot of people battle with. What will the reading be on the spring balance in diagram B? Now, what we've got to understand is how the spring balance works. And the spring balance works on a spring. When there is no force on either side, the spring will be compressed. And as soon as I apply a tension, then the spring expands. Now, the expansion of the spring can't happen with a force from one end only. It has to happen with a pair of forces acting on either ends of the spring. Now, the spring is then adjusted to read a marker. So if the marker was set over here and it was at 0 newtons, because there's no forces on either side, now it's moved. And I hope you can see that in this way we can actually measure the tension in the rope. It's kind of giving us what's the force, what's the pull on either end of the spring. And so in this case, the reading, what do you think it will be? It's not going to cancel out, but it's going to be 25 newtons. Please make sure you understand that, because the spring has expanded. It's under tension. There is a force that's being applied to the spring balance. It is not zero. And I think that brings us to the end of this consolidation section of the physics for grade 11. Please make sure you go over this, and I wish you well as you prepare for your final exams.